let me just review this now. So this is involving refrigeration with two evaporators, and there is a problem here. The key, you know, the key message here is you have to know how to draw the pH and PS diagram, and at least you should be able to know the points, no, or the condition, the state, no, state or the condition based on the given problem. So state or condition, state or condition. Okay, so we will review this because I still see some of the drawings which are not correct, right? Now, so we review this, no, because I want to be more clear on this, no, rather than we are discussing again and again many other problems, but you don't understand the basics. No? So here R134 is the working fluid in a vapor compression refrigeration cycle with two evaporators. So at the outset, at the beginning, you know that it is a multi-evaporator system. It was given that the working fluid is R134A, commonly used now, no? Because R22, R12 is fastly uh, uh, declining. No? Its usage is fastly or being stopped by the regulatory body or commission, especially in the United Nations, no? Because it damages the environment, the ozone layer. So R134 is always used now, and R410 and so on. Now, the next is saturated liquid exits the condenser. Where's that? What point is that saturated liquid exits the condenser? Can you give me the point, the number?
3.
3, right? So if you are an engineering student, mechanical engineering student, you would know that that is number 3, no? And it might help you if you are going to draw. The most common is the pH. Now we'll just draw the pH side by side with the problem so that we can see, no? And maybe we could show that pH later. Now, so here easily I can make a dome, a bell, no? Because this is the standard for the ideal vapor compression system. Right? It might not be perfect, but at least it represents. No? Now, the question now, class, is where is the saturation liquid where the condenser exits? Top or bottom? For example, here, I would there's a two line here, as you can see, no? Where is the saturation liquid condenser lies? Top or bottom?
So,
Top, yeah? Because we know that the condenser is somewhere here at the top and the evaporator is at the bottom. So at the back of your mind, you know that this is on the high pressure. No? This high pressure line, this is low pressure line. Because you know high pressure involves the condenser and the low pressure involves the evaporator. Now that is how you systematically think, how you systematically translate the problem into the diagram. So the next question is saturated liquid. Where's that? Left or right? Left. No? So here, this line, I'm going to repeat now because is the basic. Now in the board exam, it is always given. Yeah? Half half of the left is saturated liquid, meaning 100% liquid. Okay, half right is saturated vapor. That's why here the subscript are G. No, G means gas. No, example Hg, enthalpy of gas. Here, enthalpy of fluid, which is liquid. Now, so I will put here now. So here is the line. So I'll put like this. Yeah. So at this point, I will make it number. What fluid is this? Three, saturated liquid. No. So I guess my point here is how do you translate the problem into diagram? No, because it sometimes it becomes more complicated. You don't know whether it's superheated or saturated or where it lies. No. Now, what's the next? The refrigerant in the evaporators, meaning two, are 0 and negative 20. No? So the question is, how many evaporators are involved? How many? Two. No. What are the temperatures and where are they located? That's the next question. The temperatures are 0 and negative 20. So where would you place the 0? Where would you place the 20? So I'll be using another color so that we will be more clear on this. Now I would like to be clear on this. I'll use another color. No, the evaporators are two units, and the problem gave us hint or tip. One is 0, one is negative 20. Which is higher, 0 or negative 20?
Yeah. Yeah.
0. No? So 0 and negative 20. So if I would put another evaporator na somewhere here, for example, here, I know that this is 0. How do I know? And I know that this is negative 20. How do I know that? Because negative 20 is the lowest point, no, lowest part of the pH. No, as the pressure goes high, the temperature also goes high. When the pressure goes down, the temperature also goes down. So here, I know that the lowest temperature is negative 20 because that's the lowest pressure. Yeah. If I have a low pressure, that will give a low temperature now because of ideal. Now, what's the next move that I can draw? Look at this. Yeah? Saturated vapor exits each evaporator. So this is evaporator 1. No? Ay, sorry. So this is evaporator 1, the 0, and this is evaporator 2, this one. Yeah? How do I know that I have to do something here? So these 2 points are the exit of evaporator 1, exit of evaporator 2. No? How do I know that I have to put a kind of mark here? Because it is being given in the problem, saturated vapor exits each evaporator. We already know that this is the middle critical point, and this is the vapor, no, vapor line. No? So when it exits, no, when the evaporator exits, now this the discharge of the evaporator, I know that this is touching the evaporator, the saturated vapor line. Understand? Do you understand, class? So this is evaporator line, no? Evaporator exit, saturated, meaning gas. So meaning here, the quality is 1 or the quality is 100%. Now by percent is 100%, by proportion it is 1. Now the question is, what is the quality here at point 3?
Zero.
0. Yeah. So at point 3, the quality is 0. Why? Because X is the quality, no, of refrigerant or steam. If you are in the power plant, that is steam. But we are not in the power plant. We are in refrigeration. So there's no water here, but rather refrigerant that becomes vapor. From liquid, it becomes vapor. So Quality, the other name for quality is dryness fraction, no? So here, there is no dryness here because it is wet, basa, no? So if basa to, pure liquid, no? Means saturated liquid, zero. Here is pure vapor, 100% vapor. There's no amount of wet here. There's no wetness here. That's why it is 100%. When you go beyond the saturated vapor line, it becomes superheated. Meaning, superheated region is a region where the temperature and the pressure is higher than saturated. Now, beyond saturated liquid, what do you call? How do you call this region? This region here. Anybody knows? So the term is subcool. Subcool. Sub means under, a submarine. Huh? Sub is the prefix meaning under, no, or below cooling. Below saturated vapor is subcooled. Okay? So you have to have a subcooler or another valve to cool the saturated liquid. No, that's why it becomes cold, subcooled. No, so meaning if you have a subcooled process, it will go beyond like this. It will go beyond, then it will go here. Okay, subcooled. Okay, but now we don't have that process of subcooling. No, so I will erase that. No, we don't have subcooled. I will erase, and let me go back to our discussion. No? So we know that point 3 is the saturated liquid line. Okay. Now, from I'm trying to describe the problem based on sequential order or chronological order. No? Now, what is the process from 3? The first evaporator has a refrigerating capacity or refrigerating effect of zero point 0.9, and the second evaporator is zero point 0.8. Now it's asking the requirements and the parameters to be solved. Number one, mass flow rate of the refrigerant through each evaporator, meaning evaporator 1, evaporator 2. What is the refrigerant? And then what is the net power to the cycle? So look at this now. After 3, the question is, after 3, what do we have? After 3, which is the saturated liquid, what do we have?
Evaporator.
Now, before evaporator, what do we have? What component is that?
Yeah, expansion.
Expansion valve, no? We need an expansion valve to reduce the pressure, to regulate the pressure and flow of the refrigerant because the evaporator can only absorb low pressure and low temperature. So here, what is the process involved in the expansion valve? What is constant here in ideal vapor compression? No? Because we're talking of always of ideal, no? Whether it's in power plant, diesel power plant, we refer to the ideal. And in ideal vapor compression, the process in the expansion valve, we have a constant. What is that? Constant enthalpy. No? So enthalpy, look at this. Now, in our diagram, enthalpy is in the horizontal. And if you read that, you read that vertical. No? So here, to have a constant enthalpy, I would have a straight line here, right? It might not be straight based on my hand, but we have a straight line. So what is this? It touches the evaporator 1 at point what? Point 4. Now, the question is, what is happening at point 4? Some of the liquid is going to the evaporator 1, and some of the refrigerant also, the residual goes to down, no? Yeah. Understand? So there are two directions. One is going to evaporator, the one, and the one is going to evaporator 2, because there are two evaporators, right? So another expansion valve is here. So when we have expansion valve, we know that the process here involves constant enthalpy. That's why we have a constant enthalpy here going down. No? Constant, look at this, constant, constant, look at this, yeah? So you will read here the enthalpy, yeah? For example, what's the enthalpy? 100 or 1000, blah, 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 the constant. The pressure is going down, 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 but it maintains a constant value of enthalpy. Okay? So right now the pH diagram is trying to is beginning to have a clear picture, right? Now, so we have 3, 4. So we call this as 5, 4 and 5. Based on the drawing, look at the drawing, no? So between evaporator 1, the process is 4 and 5. So here I would like to call this as 5. How do I know? Because that is the exit of the evaporator, which is saturated vapor. Now, another evaporator, which is located at the bottom, 7, 8. So the exit of the evaporator 2, evaporator 2, which temperature is negative 20, is 8. Here is 8. 8. What is number there? What number is this? 7. Okay? Now, on the right side of the pH, that is our problem. And it's a little bit tricky, no? So if this is 8, what is happening? What is remaining? What are the other numbers that we don't have yet? So here is, what is this? 6 and 1. Now, the question now is, where is 6 and 1? 2 is there, no? We know that 2, what is the condition of 2? At the exit of the compressor, we know that it is high pressure, no? Because here, look at this, high pressure. From the evaporator, it goes to the compressor, it is high pressure region, and we know that it's superheat. How do we know it is superheat? Because it is beyond the saturated vapor line, and once it enters, now before it enters to the condenser, it is really superheat because there's an extra, there's an extra amount of energy being transferred to the refrigerant because of high pressure. The work of compression, because it is compressing the refrigerant. Once it compresses the refrigerant, the temperature is also gaining its value, becomes high. It is more than the saturated vapor, so it is superheat. Now that's why it is in the superheat region now. So easily I can say that it is number 2, right? I'll put back the red. Green. So easily, class, I can say that it is number 2. No? Any question? Please interrupt me if you have a question, right? So I would mark this as number 2. Okay? Superheat. Okay? Now, 2, 3, 4, 5. What is this? The other 6 is over there. 7, 8. What is remaining now? What is remaining now, class? 6 and 1, no? Before you can draw it in the pH diagram, you always have to look back at the drawing, no? Because this is a drawing, and if you are an engineer, no, an intelligent, smart engineer, you would know to translate this. You would know how to translate this in the pH or TS. What is between 5 and 6?
Expansion.
Expansion valve. What is the purpose of expansion valve? To lower the pressure. Now, it is logically situated there or mounted there because here you have to lower down. You will have to lower down the pressure. No, meaning lower down the pressure because it has another evaporator. No, the evaporator too is operating at a lower pressure. So before they go to the compressor, they should mix. No, the term is mix. Where's the mixing point? Here, no? The mixing point is here at 1. So look at this, no? So this portion here, I would put a mark, no? I would put a mark here. So this is the mixing point at 1, no? Nakikita niyo ba class? Ito. So this here is 1. Na ito 1, no? Papunta sa compressor. So paano mo yan ita-translate sa pH, no? You know that 5 and 6 is constant enthalpy. How would you do it? So what's happening in 5 and 6 is what? The pressure is going down at enthalpy is constant. So here, you can represent now. I would draw a line here. How to make a pressure constant line? Straight lang. Okay? So pag binaba ko to, if I make it down, no, if I make it somehow down, ito yung 6. No? Nasaan yung 1? Tanong, nasaan yung 1? Where's 1? In between 8 and 6, at the right of 6, or at the right of 8? O, ganito ha. Bababa ko to. So, ito is 8. Ito ay 6. Nasaan yung 1?
Between.
In between, no? Ito yung 1 in between. Because, as you can see here, no? Pag binaba mo to, 5, 6, then constant enthalpy, ito yung enthalpy niya. So, ito yung 6, ito yung 8, no? Ideally, dapat dito yung 1 sa may 8, no? Pero hindi nangyari. Why? Because nagkaroon pa nga tayo ng expansion valve, no? Na expansion valve. So, yung 1 mo, mamumove lang. Move a little bit farther right, down, right toward of the exit. No? Kasi exit na to ng evaporator eh. So, exit ng evaporator, hindi naman pwedeng lumampas doon sa expansion valve, di ba? Pag sinabi mo expansion valve, lalampas, no? Magiging iba na yung drawing natin, no? So, dito, ang 1 ay nandito in between. Ito. Yan, no? So, 1. No? So, ito yung 1. No? So, from 1 to 2, yun yung work of compression. Doon nangyayari yung work of compression. Ito, 1, 2, and 1. No? 2 and 1. Doon nangyayari yung trabaho ng compressor. Okay? So, ganun yan. So, kung ito yung mga drawing nyo, tama. No? Kasi nakita ko yung mga drawing nyo iba. No? 1 nasa gitna. Okay? So, nilinaw ko lang. No? Nilinaw ko lang. Ito. I'll forward this because it will take so much time. If we discuss this, we will be no longer in a position to discuss the topic na evaporator. Since we already know this, ilagay ko na lahat ng mga table. I put all the tables, I put all the graphs, so you can more or less follow this, right? So, ano ko lang, no? Kinorek ko lang, no? I-review ko lang, ha? I-review ko lang para, pupunta na tayo sa evaporator, no? So, look at this. When you are trying to read the problem, you can easily plot, no? So, how do you plot the problem? You can easily plot because here, there are points to be considered, no? At point 3, what is point 3? Saturated liquid. How do you know it is saturated liquid? Because it is the discharge of the condenser, na saturated liquid. It is said in the problem, saturated. Now, the other points that are easily plotted is what? 5 and 6. How do you know? 5 and 6. 5 and 8. How do you know this? Because this is saturated vapor. 8 is also saturated vapor. How do you know? How do you know that they are saturated vapor? Because it is given in the problem. If you read the problem carefully, saturated vapor, it is said saturated vapor. Saturated vapor exits each evaporator. So you know that they are saturated vapor, no? Saturated vapor. Yeah. Okay. Now, so we have plotted this. No, we were able to plot this. We were able to plot this. We were able to plot this. Now, how do you know that 4 and 7? 4 and 7, it's easy to know because in between them there is a device called expansion valve. Expansion valve. And the expansion valve, the duty of the expansion valve is to lower the pressure, lower the flow, to regulate the flow at constant enthalpy. So look at this, yeah. So this is P, P, this is H. So look at this, straight, no, straight. So only the enthalpy is here. Now it's not changing. The pressure is lowering down, the pressure is going down, the pressure and temperature is going down, but the enthalpy is constant. So you know that this is 4, this is 7. How? Because 3, then 4. 4 to 5, no, this is evaporator 1, then 7 to 8 is evaporator 2. No, evaporator. So this is straight, right? This is straight because this is constant enthalpy process. So you know what we are lacking is 1 and 2. We know that 2 is somewhere here. No? Somewhere here is 2 because it is in the superheated region. After the compressor, at the discharge port of the compressor, sa labas ng compressor, superheated yon. Now, superheated because by virtue of high pressure, no, the pressure is going high, and it follows in the ideal gas temperature is also going high, right? So it is there in the superheated region. Now, before it enters, so my question is, where is the entrance of the condenser? Here. That's the entry or entrance of the condenser. Before the entrance of the condenser, there is this line, no? So there's line that is superheat. So before it enters the entrance of the condenser, you should have this portion. You need to do something, no? You need to de-superheat. No? You remove the superheat uh, condition, not the superheat. Once you remove the superheat, it becomes now the saturated. So this point is saturated vapor again. No? So this point is saturated vapor. Yeah, this one is saturated liquid. Okay. Now, what we're lacking right now is this 6 and 1. How do you know 6? 6 is no between 5 to 6. It has a constant enthalpy. Yeah. Why? Because there's another valve mounted. I would like to show you here. There's another valve between 5 and 6. No? Between 5 and 6, there's another valve, maybe back pressure valve or another expansion valve. But the point here, the point of those valves is to lower the pressure coming from the first evaporator down to the second. So that when they meet at the entrance of the compressor, they are in the lower pressure. So that will only happen going down, no? Because the entrance of the entrance of the evaporator is at this, no? Look at this, no? So this evaporator 2 should have the entrance, no? At this line should have the entrance of the compressor, no? So what will happen is like this, right? So this is 8. This is from 5, it goes to the 6. Then this is 1. No? Then 1 goes to 2. Okay? So that is our main point there. No? So, wait, let me go back to our, what is happening? Hold on. We're trying to get you back into the meeting. Carl, may internet ka? Ba't nawala sa akin? Bubunutin ko? Bunutin ko? Lahat ng wifi? Lahat ng wifi? Isa. Hindi. Nasili nga isang cable. Wala. Ah. Hindi ba siya naman gumagawa?
Yari.
Hello, hello?
Crash
Kita mo kayo dyan, Bit.
Hello, Crash. Hello, hello. Nawala ako eh. Sorry ah. Okay na? Hello?
Apo.
Okay, sorry. So we go back to the presentation, no? So maliwanag na 'yun ha. Sinasabi ko ay ganito, no? Ito 'yon, no? So balik tayo sa pH, 'di ba pH 'yon? Balik tayo sa TS para naintindihan yung TS. So sa TS, alam natin na ang constant here at the TS, ang constant natin ay 1 and 2, no? So how do we know it is 1 and 2? Because S nga eh, di ba? S is ito. So ang enthalpy mo ay nandito, 1 and 2. Look at this. Ito. 1.
Sir, wala pong share screen.
Wala ba? Sige. Share ko muna. Sorry. Kasi ni-reset ko nga pala, no? Nag-reset pala ako. Sorry po. Here. Yan, okay na? Okay na,
Apo.
Adel, yan. So, we have been discussing the pH. Now it's TS, now temperature entropy. How do we know the constant in the TS? The constant in our vapor compression is the process happening at 1. 1 is the entrance of the entrance port, no? Yung port, yung pinagkakabitan ng linya, ng tubo, no? 1 to 2. Between 1 to 2, the entropy is constant, S equals C. So, if you go to the TS, you know that 1 and 2 is constant, no? So, 1 and 2 is 1, no? Straight line. 1 and 2. Okay? Now, between 2 and this, no, it goes down to the saturated vapor because the superheat. Now, the superheat means you should lower the temperature and pressure. Look at this T. What is happening here now? At this slope, temperature is going down up to here. No? And when the temperature is going down, the pressure is also going down. No? So here is the saturated vapor line. No? So all this, all the half right saturated vapor line. This half left at the TS diagram is saturated liquid. Basa to, basa na saturated liquid line. No? Now, what is constant in 3 and 4 according to the diagram? Ito. Anong constant dito, class? Anong constant dyan? T, di ba? T, ayan. Maliwanag naman, di ba? T, 3 to 4. Ay, 3 to 4. 3 lang, no? 3, kasi ito yung 4. So, between 3 and this line, bago mag-2 ay constant. Now, tingnan mo. So, pag tinignan mo yan sa pH, ay no, 3, no? Yung 3, ito yun, no? Constant yan, no? So, dito is temperature is constant because the temperature is like this, no? So, going vertical, constant temperature, tapos curve. So, dito rin, no? Ganon. So, makikita mo rito, dahil constant enthalpy siya, di ba? Constant enthalpy siya. So, ang temperature dito, no? Constant temperature. Yan. Ito rin, no? So, constant temperature. Tapos, ito sa vapor. Ito sa superheat na, yung 1. Tapos, yung 6. No? So, may tatlo tayong superheat. No? Yung 8 ay saturated vapor. Ano yung mga tatlong superheat? 1, 6, tsaka 2. No? nasa superheat region sila. Tingnan nyo. 2, nasa superheat. Yung 1 sa evaporator, superheat, saka 6. Okay? Now, sa TS, tingnan nyo, sa TS between 3 and 4, ano to? Ano tong line na to, class? This line. 3, 4, and 7. Ito, sa TS, pag nakakita nyo to, pag ganyan line, curve. Yung 1, yung 6. Pag yung mga curve ay ganyan, ano? Anong curve to? 3, 4, 7. Enthalpy is constant. Tinan mo dito sa pH, no? Kaya, pag nag-analyze kayo, dapat side by side, no? Para naintindihan nyo, ano yung itsura sa pH, ano yung itsura sa TS. No? So, look at this. Pag tinignan nyo sa pH, no? 3 to 4, constant ang enthalpy. 4 to 7, constant na naman ang enthalpy. Ayan, no? Ito lang yung enthalpy, di ba? Ito lang yung point. Ito naman, 5 and 6, constant yung enthalpy. Ito yung enthalpy nun, no? So, dito naman, 3, 4, 7, constant yung enthalpy. 5 and 6, no? Pag tinignan mo to, 5 and 6, constant yung enthalpy. No? So, that is how we read the pH and pH. No? So, everything is okay except yung mga representation lang sa chart. No? So, ito yung galing sa software mismo. Look at this. No? Para ito. Ito yung galing sa software na diagram. So, here, 3, 4, 7, ano yun? Enthalpy is constant. So, 5 and 6, enthalpy is constant. No? Then, 7 and 8, ano nangyari dito? Pressure is constant. Another, 4 and 5, pressure is constant. Why? Because they are heat exchangers. Ano yung heat exchangers? Yung evaporator, di ba? So, evaporator 1, evaporator 2. Between 3 and this saturated point here at the vapor, pressure is constant. No? Ito, up to here, pressure is constant. Makikita mo dito, di ba? Ayan, no? No? Kasi, pressure is constant, no? Between 3 and the saturated. Makikita mo yun sa pressure enthalpy. Ayan, 3. Between 3, saturated vapor, and up to here, saturated liquid, pressure is constant at 826. So, ito rin yun. 3 and this line is pressure is constant and also temperature is constant. Kasi TS natin, di ba? TS. So, straight lang yung temperature. Oh. Di ba? Ito rin. 0 degrees ang temperature dito. Ito, negative 20 between 7 and 8. Pressure is constant and temperature is constant. Ayun, kita mo, di ba? Pressure to. Pressure, enthalpy. 7 to 8, constant pressure up to here. 4 to this 5, pressure is constant. Ayun, P. Diba? So, ganun yun. Okay? So, ito yung mga diagram, tapos ito rin yung mga calculation. No? And then, I put the table for your reference, no? And then the pH. I downloaded the pH diagram, tapos pinlat ko, no? So, look at this. Ito lang, tapusin ko lang to, no? So, we have this saturated liquid, no? Saturated liquid. Tapos, evaporator 1, di ba? 0 degrees centigrade, 293 kilopascal. Then, evaporator 2, negative 20 degrees centigrade, constant pressure. Ito yon 133 kilopascal, no? So, ang gagawin mo dyan, ibababa mo lang, no? Kasi constant enthalpy. Tapos, eto, lalampas doon. Then, eto, meron dito yan. No? Ayan, no? Ito yung 0.8. Di ba? 0.8. No? Tapos, 0.8 yan. Tapos, somewhere here, yung 1 tsaka 2. No? 1 tsaka 2. No? So, pagbawa, ito yung 8. Ito yung 1. Sorry, ito yung 6. No? When you try to move down from this, no? Ito yung 5. Di ba? Ito yung 4. Ito yung 5. When you try to project a vertical straight line from 5, you will have the 6. And 1 is between 8 and 6. So, ito yung 1. Ito yung 1. Ito yung 6, no? Kasi ito yung valve, eh. Ito yung valve. between 5 and 6. So from 1, which is also superheated at this point, papunta sa 2. No? Somewhere here yung 2. Nandito, no? Kasi you will get a constant entropy. Tapos, you will given pressure. No? Ito, 863 Pascal. So 863 kilopascal. If you have a pressure, if you have an entropy, di ba? Ito yung constant entropy line. Constant entropy line between 8 and 6 is 1. No? You have a pressure, constant pressure, and then entropy is constant. You will get this point, no? Mag-meeting point. Then i-project mo lang. I-project mo lang pababa, makakakuha ka ng enthalpy, no? So anong enthalpy natin dun sa 2? Sabi diyan sa enthalpy at 2, enthalpy at 2 is what? Ito, no? 432.89. No? So makukuha mo naman 'yon, no? Or somewhere in that region. Okay? I think this is already okay, no? Kinorek ko lang yung mga ano natin, no? So we go now immediately to our class. Now we have time remaining. I would like to discuss yung evaporator. So wait, I'll just pull out. So class, can you see the evaporator, the slide? Nakikita ba, class?
Yeah.
So our topic is now the evaporator. Now, the evaporator is one of the major components in the refrigeration system. So there are other refrigeration systems, and I think you have to read. Now you have to or you research by yourselves because we don't have time. Next week is already the final exam because much of our time were eaten up by the no classes because of the typhoon, no because of the maintenance of internet and others. Now, but here they are not included in the board exam normally. The only one included always in the board exam is the vapor compression system, the one that we are discussing from the beginning. But my point here is there are other system in the refrigeration like vapor absorption, air cycle refrigeration, steam jet refrigeration, then cryogenics, meaning the science of very cold temperature, very cold and low pressure cryogenics, and then the other is solar refrigeration. So from vapor absorption to solar, please read by yourselves. And I would like to, I would make slides to complement that. Then I will put in the portal. But our concentration is the vapor vapor compression system with the major components. So without further ado, I would like to show this. Now, vapor compression system again is a compression system is a refrigeration system that compresses the refrigerant, no, that becomes vapor after the compressor. So here, I mean after the evaporator. So here the vapor the vapor is here in the evaporator before going to the because this one is like a kind of counterclockwise. Yeah, look at this, counterclockwise. So the evaporator, the refrigerant is here. It becomes vapor before it enters the compressor. It is in the vapor state. No, that's why vapor compression. It compresses the vapor. It compresses the vapor. It becomes superheat. No, at this side. That's why this is high pressure side. No, if you got it half, then it's low pressure. No, so where is the high pressure? It starts at the discharge of the compressor at the outlet. Now outlet discharge is the same vapor. Now the vapor is compressed, the vapor refrigerant. Then it goes to the condenser. Why? Because the condenser should reject the heat so that the refrigerant should become condensate. When we talk about condensate, it should be liquid form, right? So when the refrigerant comes here, it becomes It becomes liquid because it's long enough. Now, normally 40 feet and others, no? So this line is long. It is just coiled, no? So heat is rejected to the environment, but the liquid is still high pressure. That's why here, no? Half. Then it goes to the expansion valve so that the pressure could be lower, no? So you lower the pressure, you lower the temperature, and then the amount of refrigerant is also regulated so that when it goes back to the evaporator, we have a low pressure, low temperature uh, refrigerant in liquid form, no? Liquid form to, no? After this is liquid, high pressure, then you lower the pressure. This liquid should be translated again so that it will become vapor, no? Vapor because the compressor only absorbs vapor. When there's a liquid in the compressor, it will damage the crank, the crankcase, the cylinder, and others. No? So only in the vapor. So the system goes on and on. That's why it becomes cycle. No? So that is the refrigeration. Now, I would like to test your knowledge. Where is the can you give me the name of this? Now, so we know that this is the compressor, right? And we know this is the what is this? Expansion valve. In this case, the capillary. No, when you are dealing with small refrigeration system, normally you don't use expansion valve. No, you just use capillary tube. So in the capillary tube, so here in the capillary tube, at the back of your refrigerator, there's no valve there, no? Like a big expansion valve. Capillary tube, no? And there's an orifice and spring inside, no? By virtue of Bernoulli and by virtue of Venturi meter, no? When the area goes small, what happens to the velocity? It becomes high, but the pressure drops. Yeah, that's why pressure dropper or pressure reducer, no, because of the constriction in the diameter, no. So how do I know where is vapor and where is condenser and where is the compressor? How do you know that? Where's the condenser and where's the vapor evaporator? So if it is clockwise, no, it depends on where are you starting and what is your direction. So if this is the compressor, after the compressor is what? After the compressor is what? After the compressor is condenser, right? So after the compressor is condenser, then high pressure liquid is here. High pressure liquid, it goes to the capillary tube or expansion valve because it should lower the pressure. Pressure should be lower, temperature should be lower, and flow should be regulated. The amount of superheat or the refrigerant should be lower so that when it enters to the evaporator, it should have a lower temperature and lower pressure. No? So then when it goes to the evaporator, it is still liquid, right? Liquid, that's why it should be evaporated. So here it goes here to the coil. Now it becomes, no, the evaporator absorbs heat. No, all the heat in the surroundings will be absorbed. That's why the refrigerant inside the evaporator tubes becomes vapor. No? So the vapor refrigerant is only absorbed, no, the only one absorbed by the compressor. It is absorbed there. It is being compressed. No, after it's being compressed, it should be taken out. No, work of compression is happening here, and then it should be taken out so that it will be condensed again. No? So that is what is happening. Now, so let me. Are we still have we recorded this? Are we recording this? Hindi pa natin na-record, ano? Kasi nag-reset nga pala, no? So ngayon na natin na-record. Okay. Uh, now we continue. So we continue our topic, and actually our topic is this, right? So we already know this. and then yeah, high pressure side, no, and then low pressure side we already know now. Then the ideal versus actual is here, right? So ideal is this, right? So ideal refrigeration system, just a review is this, now before we go to that, yeah. So ideal refrigeration system is here, right? So here, the only thing you have to know is this, right? So here, it should touch in the saturated liquid line, yeah. And then that is the saturated liquid line, then half is the saturated vapor line. Yeah. So here. So saturated liquid line, this one is constant enthalpy. This is constant enthalpy, constant pressure, then entropy is constant. No? That this is saturated vapor line, no? The ideal. So when you go here, you go beyond here, that is superheated. Then when you go beyond here, subcooled, then you are in the actual, no? In the actual practice, subcooled and sometimes superheated in the entrance of the compressor, like this, yeah, like the one we have a while ago, like that, yeah. So here, sometimes it goes beyond because of the some cooling, yeah. So the refrigerating effect is being improved, no? The refrigerating effect. If you subcool, the refrigerating effect in the evaporator is being improved, no? So that is it. Now we focus now in the evaporator, yeah. So evaporator, we would like to focus there, no? Evaporator is our focus, no? Evaporator absorbs heat. What is the function of the evaporator? A device in a process used to turn the liquid from a chemical substance such as water or refrigerant into gaseous vapor. So from the term itself, evaporator is the input is liquid and the output should be in gaseous or vapor form, right? That's the purpose of evaporator. So what are the forms or types? Anong itsura? Anong itsura ng mga evaporator? Yan. Saan ba nanggagaling ang lamig sa
Sir,
iba?
nawala po yung share screen.
Ano na? Ano? Wala sa screen? Wala sa screen class?
Yeah.
Sandali. Hindi ko ba na-screen? Yan, meron na? Meron na class? Hello? Okay na? So this the evaporator. I would like to show you, no, because different form, no. So if you are in the cold room, no, sa mga factory, sa mga planta ng mga electronics, you might see this kind of evaporator. But if you are in the residential, for example, in your house, in your neighbor's house, I would like to ask you, what is the kind of air conditioning unit? What's the name? So in the houses, no, or condominiums, the one that is being used is box type or window type. Would you kind enough to tell me where is the evaporator? Where's the evaporator located? In front or at the back? Tell me. Where is evaporator located? In front? No? Ito ba? In front or back? What's the answer? Ayan naman, oh. Kita na, di ba? Evaporator coil. Nasa harap. Ang nasa likod ng mga aircon na nasa bahay nyo ay condenser, kaya mainit. Heat rejected, heat absorbed. Look at this, no? In front. In front. Evaporator is in front. Heat is absorbed. At the back is what? Condenser. Condenser. At the back. Heat is rejected. So when you go at the back of your air conditioning unit in your house or in your friend's house, Now, mainit. It is very hot at the back because heat is being rejected, the heat from the refrigerant, so that it will become in a liquid form. It will become condensate. Heat should be removed. No, heat should be thrown into the atmosphere. Now, here is another evaporator, very very far from the one. No, so here is the evaporator. Look at the 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 form, no? So this black thing here is the evaporator. So this is the evaporator of the chiller, right? Evaporator of the chiller, and the other side is the condenser. Yeah. So the big one is the condenser. So that is the chiller. Now this is the evaporator of a made in China. No, I just researched this morning. So this is the evaporator. So could you tell me where's the suction and discharge? Where's the suction and discharge? So there are only two ports, right? Or the tubes. This one and this one. Where's the suction? We would say that this is the suction and this is the discharge. Why? You can see from the diameter. Yeah? So the size of the diameter. Always, no, remember class, always the diameter of the suction is big compared to the discharge. No? So this is the evaporator of split. You know the split aircon. Why do we call this as split? Because the indoor, no, indoor unit and the other is outdoor. Indoor unit, ang nagpapalamig ay evaporator. Nasa loob yan ng kwarto ng mga building. Sa labas, nandun yung condenser kasi doon tinatabo yung mainit na hangin. No? Condenser, Q rejected, outdoor unit. Meaning outside. No? Outdoor unit, indoor unit. No? So you can see that in the building or big houses. Right? So here is the Ford Explorer evaporator. So where's the suction and where's the discharge? So if you have a Ford Explorer, oh, that's a very expensive car, no? Maybe 3 million to 5 million, no? Easily you can identify the suction. Where is the bigger port? Here, right? So this is the suction port of the evaporator. The discharge is here. No? Why is the suction always higher? Because it needs to have a bigger input of volume of refrigerant. No? Otherwise, if it's only equal or it's less, there will be more pressure drop. Yeah? Because pressure will drop. So pressure drop is a function of length. Mahaba yan, di ba? Length. So the longer the line, the more pressure drop will incur. And the bends, ito. Di ba? May mga bends. 90 degrees, 180, parang elbow, no? So ang tawag diyan ay bends ng fittings. So it will incur pressure drop. So kung maliit ang suction mo, paano mako-compensate yung mga pressure drop? So it should always have a larger diameter yung suction. Okay? So the others are here at the aircon. Look at this, no? So I would like to focus here. Yeah? So this is the evaporator of the Ford Mustang or the Suzuki or the Toyota. So these are the evaporator no, in front of the panel, no, in front of the driver. Kasi yun ang nagpapalamig sa driver at sa mga pasahero. No? Yung condenser naman nasa labas kasi binubuga niya sa atmosphere no, going outside ang mainit na hangin. No? So there are other evaporators. Now, don't think that evaporators only used in refrigeration system. There are other evaporators and they are used in industrial processes like this one. No? Falling film evaporator, rising film evaporator, they are used in sugar manufacturing process. And there are evaporators, many evaporators used in petrochemical, no, gases, oil and gas, petrochemicals, paggawa ng alcohol, ng mga beer, no, brewery, alcohol, mga pabango, lahat ng liquid processes it involves evaporator. So this case, it is multiple evaporator, no? So, but our focus is the evaporator used in the in the refrigeration system. So now the capacity of the evaporator, what's the capacity of the evaporator? The capacity of the evaporator is measured in what? Tons, no? Tons of refrigeration or kilowatt or horsepower, right? Like the example we have, no, zero point 0.8 ton, zero point 0.9 ton, no? So you can convert the ton in horsepower, you can convert the ton in kilowatts, right? So ano yan? 1 ton is 3.516, no? Or 52 kilowatts, no? Ton of refrigeration. PR, TON, no? Or RT, refrigeration ton. So this is what we are going to solve, and then in the imperial or English units, it is expressed in this BTU per hour, no? And even now, always it is always used in two systems, no? BTU per hour or joule or no? Or kilowatt, no? So those are the units of the evaporator capacity. Now we go to the calculation. How do you calculate the heat in the evaporator? How do you do that? What's the formula? We know that the evaporator is a heat exchanger, and when we say heat exchanger, it allows the exchange of heat, no, from one form to the other. For example, from air going to the metal, or from air cooling the or absorbing the heat from the air to the fluid inside the tube of the evaporator. So, for example, refrigerant. Paano ba na-evaporate yung refrigerant? Kasi may mainit na hangin, or there are hot substances. For example, in your refrigerator, the meat, no, yung karne, vegetables, heat, water, pupunta yun sa tube ng evaporator, and the refrigerant is boiling at a very low pressure and low temperature. No? Kahit mababang temperature, magbo-boil agad. So, hindi lahat ng nagbo-boil ay mainit. No? Kasi ang nakikita lang natin araw-araw ay tubig. Pag nagpainit tayong tubig, nagbo-boil. No? Pero hindi lahat ng nagbo-boil ay hot. Refrigerant is very low pressure, low temperature, but it's boiling. Meaning it changes its phase or state. No? Ang tawag doon ay latent. No? Latent heat. No? So, from liquid refrigerant to the vapor at a very low temperature and pressure. So that's the property of refrigerant. Now, we go to the formula, which is QAUD. So, yung Q is just the heat, no? The heat transfer, or the heat energy transferred into the surface, no? And it is expressed in AUD. What is A? A is the surface area of the evaporator tube, no? So, ito yung mga tubo ng evaporator, and then to increase its area, merong tinatawag na fin, no? So, look at this, no? So, this is the evaporator. Kaya humahaba yan kasi coiled, na? Ngayon, yung mga tubo may fin. If you go at the back of your aircon, no? At the back of the aircon and in front of the aircon, so there's a tube, but this tube is merong mga ano yan, may pin, no? Ayun, no? May parang nakabalot. No? So the purpose is of the fin is to increase the surface area so that the heat transfer becomes more efficient. Now, fin tube, no? Ang tawag dyan ay FIN or fin, no? So area outside surface of the evaporator, both prime and fin. The overall conductance factor is BTUR, square feet outside surface, no? Ito, overall conductance factor, degree Fahrenheit. And D is the logarithmic mean temperature difference, no? So D is like a delta T, no? Temperature, or TD. Some are using delta T and TD, no? D, difference, temperature difference. So that's the formula. Now Q equals A U delta T. Others are using delta T, others are using D difference, others are using TD, temperature difference. No? So, but the main point here is that this is just the logarithmic mean temperature difference in degrees Fahrenheit or centigrade, depending on what unit are you are using, between the temperature outside the evaporator and the temperature of the refrigerant inside the evaporator. No? So if this is the evaporator, so outside, no, outside ng tubo is this, no? So outside the tube is air. Air is in contact with the surface of the tube. But inside the tube is the refrigerant, which is in the lower temperature or lower pressure state. So the temperature at the outside, for example, the air, is higher than the temperature inside the tube of the evaporator, which is the refrigerant. Always like that. The refrigerant has a lower temperature than the outside, which has higher temperature. That's why there is a temperature difference. Because if there's no temperature difference, there would be no heat transfer, right? So now, there's another thing that we have to consider. That is U. What is U? U is the overall conductance factor, no? So conductance. So if you take up control system engineering or modeling, you will know this conductance, no? But normally in electrical, for example, resistance, diba? Conductance, impedance, inductance, no? So it is translated into fluid. So fluid also has resistance. Fluid also has conductance, no? And others. So what is the formula and what is the relation? The relation of U is inversely proportional to R. What is R? Thermal resistance. Okay? So it's a bit complicated, no? But we are rushing time. I'm sorry for that kasi we have done we have used up much of our time in the typhoon, no? So the important thing here is, look at this. The U is inversely proportional to R. And what is R? How do you know the resistance? Every material has resistance. And how do you increase the resistance? Meaning, if your U is, if resistance is increasing, the U is decreasing. Meaning, the more insulation, no? The more insulation, halimbawa yung tubo, binabalot mo yung tubo o yung room, nilalagyan mo ng mga insulation, ng mga foam, yung mga bintana para hindi lumabas yung init, no? Lalagyan mo ng mga styrofoam, saka yung mga Teflon or yung mga insulation. So pag tumataas yung insulation o dumadami, kumakapal, no, thickness ng wall, bumababa yung conductance. Okay? So bumababa yung conductance. That is the relation. So the formula is this: RFI times L over K and 1 over FO. So these two here, look at this. Now these two Fi and F sub O are the film, no? Conductance factor of the inside surface film. Kaya nga I inside, and the other is the conductance factor of the outside surface film, FO, outside. Okay? What is R? Ratio of outside surface to inside surface. Now, for example, outside surface, kukunin mo yung ratio, no? R is the ratio. Halimbawa, sa tubo or sa wall, merong outside or inside surface. And the other is L. What is L? Resistance to heat flow offered by the metal tubes and the fins, because L is the length and then K is the thermal conductivity, no? Thermal conductivity. Okay, so that is the formula, and I think we could have some problems, no? So logarithmic temperature difference, we already know that there's a difference between the outside film and the inside film. So there are tables given, no? In the lecture, I have forwarded, and also this one I will forward to you this. There is this mean temperature of air passing through evaporator. Now, it's a bit dark because I only use the camera. I just bought my scanner a few days ago. But this is the graph showing the mean temperature of air passing through the evaporator. So there's a formula for the difference. Now, D is the arithmetic mean difference. Now, arithmetic mean difference. PE is what? Temperature of the air entering the coil. TL is the temperature of the air leaving the coil. No? So, entering, and leaving the evaporator coil. No? So, ganito yan. If this is the evaporator, this is the entrance. No? So, marami, may tubo. Tapos, lalabas. So out. Out is leaving. This one is entering. So, entering is lower than the leaving. No? In terms of temperature at the entrance is low. Temperature at the outlet is high because evaporate na nga, no? Nag-evaporate na nga. So there's a temperature difference in the two, no? Because heat, the air, the outside air transfer the heat to the refrigerant in the tube. Okay? So before the refrigerant has lower temperature and then low pressure, no? But the air, may init yung air, the hot air comes in contact with the tube. So part of the heat will go to the refrigerant, and the refrigerant will change its form from liquid into vapor, no? Because it absorbs heat, QA. The heat from the air is absorbed through the tubes, and the refrigerant liquid becomes the vapor. That's why it is evaporator. No? So the temperature of the air leaving the coil, the temperature of the refrigerant in the tube. So there is a outside air, then it comes in contact with the tube. At the tube inside is the refrigerant. No? So you can see the temperature difference there, and then mean, because it is average. No? Mean means average. Mean. So there are two involved data here. One is outside air and the other is the inside refrigerant. No? So to get the mean, it is divided by 2. Okay? So now there are others here, no? For example, depending on the row. For example, row 1, row 2, row 3. So column, row. So for example, 3 row. 1, 2, 3. So 1, 2, 3 row. Then exit, no? So out. Ito in 3 row. Okay? So it is only changes orientation in the drawing, no? So if you want to make it in the horizontal form, this one, no? 1, 2, 3, no? So 1, ayan, no? 1, 2, then 3, then out, no? 1, 2, 3. Yeah? So 3 row cooling, no? So may calculation dyan. There are calculation depending on the row, depending on the length. Yan. So look at this. For the values given in figure 11, that's 11, the arithmetic mean temperature difference is this. Now 40 minus 20, then 30 minus 20. Why? Because here, look at this. 40 class. 40 is here, right? 40 degrees centigrade. Then this one is 30 degrees centigrade when it goes out. How do you know it's going out? Because it is said leaving. No? How do you say it is coming in? Because it says entering. No? So how do you compute the temperature difference? You should only compute in this formula, no? The formula given in this. No? So PR is the temperature of the refrigerant in the tube. What is the refrigerant in the tube? What is the temperature of the refrigerant inside the tube? Can you see? 20, 20, 20, no? So it is row 1, row 2, row 3. So the temperature inside the tube is 20, and here, now temperature inside the tube, this is the entering, this is the leaving divided by 2. So you have a mean temperature difference of 15 degrees Fahrenheit. No? So there are equations here, and it involves this temperature difference and the logarithmic LNTD. That's why there's a natural logarithm here, no? LN, log natural. Yeah, that's why it is LNTD. So it's just the direct substitution. Look at this now. 40 is the entering, temperature entering, temperature leaving. This is the refrigerant temperature, right? And then this is the entering refrigerant temperature, leaving refrigerant temperature. Then the function is logarithm, no, natural. That's why ln, logarithm, natural logarithm, right? So that is the formula there. Okay. So here we would like to consider one example now, so that at least we are guided now, because the time is coming to an end. No? So we have an example here. Selection of natural convection evaporator. Natural convection evaporator. A frozen storage room having inside dimensions of 18 feet. No? So there's a room, and the dimension is 18 feet by 32 feet by 10. No? So 18 feet by 32 feet by 10. No? That's the length. So 10 feet. Normally 10 feet yung mga haba ng room, no? Yung width, no? So ito yung 32, no, yung length, width, no? Then 18 feet, 32 feet. No? So it's a volume, no? It's the volume of the room. Has calculated cooling load of 25,000 BTU per hour. No? So this BTU per hour can be converted into kilowatts or into tons of refrigeration. No? So merong direct conversion tayo sa kilowatts and sa ton of refrigeration. So we don't have any problem with this. No? So it's just talking about the capacity, no, of the load. The space temperature is to be maintained at 0 degrees Fahrenheit. No? So 0 degrees Fahrenheit. No? So the freezing point of ice is 0 degrees centigrade, and this is 32 degrees Fahrenheit. So it is lower than 32 degrees Fahrenheit. No? So this one is 0 degrees Fahrenheit according to this. Now, using 15 degrees Fahrenheit evaporator temperature difference. Look at this, yeah. Using 15 degrees evaporator temperature difference, select an appropriate series of plate black banks from table R-1. So we will be given the table for ceiling installation in the room. So for example, this is the ceiling, no? Pinapa-design tayo ng series of plate banks. Okay? So how do we solve that? So analysis of room dimensions 32 by 18 indicates that 4 to 6 evaporators, 2 or 3 banks installed end to end in 2 rows. No, so there are practice, no, in the practice of design, no, arbitrarily the people knows, no, if you are working with the evaporators, you would know, no. So in this dimension, no, of the room 32 by 18, we would have 4 to 6 evaporator, no? 2 or 3 banks installed end to end, no? Para palamigin yung 32 feet by 18 feet na room, tapos 10 feet yung height, no? 10 feet ang height. Yan, no? Will provide the good ceiling coverage and adequate air distribution. So may mga na-compute na yon, marami nang nagatrabaho doon for so many years, that's why they know this, no? Now, the table R-1 shows that plate banks are available in stock length of 108 and 144 inch, which is converted to 9 feet and 12 feet. Now, 3 banks, 108 inches long or two bunks and 144 would have a 24 feet, could be installed end to end in two rows and allow adequate working clearance at the end. No? So now, how do you compute this? Since the banks are already rated at the design temperature difference, no, there's a TD of 15 degrees Fahrenheit. The ratings can be used directly, and the required capacity per bank can be determined by dividing the total hourly cooling load by the desired number of plate banks. So here, the required capacity per bank, BTU per hour, that is what we're going to to calculate, no? Because it says here, select an appropriate series of plate banks. No? So, pinapahanap tayo ng plate banks para sa ganitong dimension, no? Sa room. So, we can have this total cooling load in BTU per hour, no? Yung ibig sabihin yung lahat ng init na dapat ialis, yun ang tawag doon ay load. All the heat that must be absorbed by the evaporator, ang tawag doon ay cooling load, no? Then number of bunks desired. So how do we do that here, no? So the total cooling load according to the problem is what? The total cooling load is 25,000 BTU per hour. So all we have to do is to divide that with the number of banks, no? Because according to the problem solution, mga anim na bank, na mga anim na bank ang pwedeng ilagay doon, no? So according to the solution, 6, no, sabi, no? So 3, no, tas end to end, no? Ayun, no? 3 banks end to end, no? In 2 rows. So 6 yun, no? So 1 bank, tatlo. Another bank, tatlo, no? Kasi 2 rows 2 rows, no? So yun ang ilalagay natin. So 6, 20, I think nagkamali dito, no? 25,000. It should be 25,000, right? 25,000. So this should be 25,000, no? Babaguhin natin. So 25,000 divided by 6. 25,000 divided by 6. So we will have this much, 4167, no? And 4 banks, we have 26250, no? So the total is 25,000. So let me check that in our calculator, no? So we have 25,000 BTU per hour. Now may typo error doon. Divided by 4 or 6 muna. So 41,666, no? Ito yun, 4167. Another is 25,000 divided by 4, no? For na unit. 4 bank 6250, no? So ito yun. So magkakaroon ka ng ganitong yeah, ito, no? So we have this 4167 and 6250 BTU per hour, no? At ang temperature difference natin ay 15 degrees, no? So yan ang pag-solve dyan, no? Kumbaga 4,167 BTU per hour divided by at per 15 degrees temperature difference. So yun yung ating calculation, no? So there are others, and I think we don't have time, but all we have to do is to substitute. No, most of these are direct substitution. No, another very important factor in evaporators is the CFM. What is CFM? Cubic feet per minute. Means that is the discharge volume of air. No, discharge volume of air na papasok or lalabas sa isang room. If you are going to cool it, you should know the CFM, no, cubic feet per minute. So all these are here, no? You can compute the velocity, you can compute the area, and so on and so forth. If you are designing a cooler, if you are designing a evaporator or cooler or chiller, right? So sa chiller din, okay. So first, na-discuss natin, no, yung ideal. Ideal is like this, no? So ideal is like this. No? So we have two stages, no, or line, high pressure and low pressure. At the high pressure, we can find the condenser. At low pressure, the evaporator. Okay. Normally, the discharge of the evaporator is the entry of the compressor. So we can have this like this. Yeah. No? And then here is at constant pressure, then it goes down at constant enthalpy. So enthalpy is constant. Here is the compressor. Entropy is constant. Here is the evaporator. Evaporator, what is this? Pressure is constant. Here is the condenser. No? Condenser to, condenser, pressure is constant. Okay? So I will now put the, then I will have another, let's see this, para maintindihan lang. Kasi dapat nire-review natin. Okay. So that is the ideal vapor compression system, no? Meaning from this point, which is critical point of CP, no? To the left, G yun, no? Ay, F yun, no? Fluid, no? Kaya ito, makikita natin, ito ay saturated fluid. Ito naman, yung orange ba to? Orange, no? Itong light line is V4, no? Saturated V4. Yan. So ngayon, makakuha ka nito, no? Entrance of the evaporator going to saturated vapor line. Entrance naman ng compressor, papunta naman dito sa superheated, no? Tapos i-superheat, no? The superheat, no? Because of the, filter or dryer or other devices like yung mga length ng line, it will be superheat because the enthalpy is lowering down, no? So at constant pressure, it will go to this saturated liquid line. So meron kang saturated liquid dyan, makakakuha ka ng HF, BF, SF, no? Then it will go straight down, which is pressure from here is constant, but here the constant is enthalpy, no, going down. Pressure goes down, but still at constant enthalpy, no? Hanggang makarating until it reaches the suction of the evaporator. Then again, it will go here, no? It will be evaporated, the refrigerant, and it will go to the compressor. So that will become a cycle, no? So this one is called standard vapor compression system. What about the actual? Ano talaga yung nangyayari? Sa mga actual, ang pwedeng mangyari class ay eto, no? Pwedeng start sa compressor 1, superheat na, no? Pwedeng mangyari 'yon. And then dito superheated, tapos di superheat hanggang dito, then pwedeng lumampas, no? Pwedeng lumampas sa saturated liquid line niya because naglalagay ng cooler. It's another device operating at constant pressure by ideal, pero sinasubcool. Ibig sabihin, subcool is a temperature lower than saturated, no? So subcool region is the temperature lower than saturated, no? Yan. So why do we put subcooler? Because the temperature and the pressure at the condenser is still high, no? Napakainit ng refrigerant na liquid. So we need to cool again, subcool, so that it becomes more more cold, no? Tapos pababa. So pagbaba, yan. Kasi may constant enthalpy para sa ano. So pwedeng ganyan, no? Pwede rin ganito. Hindi siya, no? Hindi siya. Tapos ganun, no? So, hindi siya constant pressure. Bababa siyang ganyan, tapos ito yung enthalpy, tapos gaganyan naman, no? So, there are many things happening during the actual, no? We can discuss it later, no? So, I just want to emphasize the role, no, yung ginagampanan ng evaporator, no? So, evaporator, what is happening in the evaporator? It transforms liquid, no? Not only refrigerant, no? Liquid. Pwedeng tubig, pwedeng alcohol, pwedeng beer, pwedeng refrigerant, no? Pwedeng gas, no? Yung mga gas na methane, ethane, na liquid. Liquid gas gagawing vapor, no? So, chemical substance such as water into gaseous form. And the evaporator, refrigerant is converted into gas, absorbing heat from the air in the compartment, no, kung sa refrigerator. When the liquid refrigerant reaches evaporator, its pressure has been reduced. No? So, bababa, dissipating its heat content and making it much cooler than the fan air, no, blowing around it. Mas malamig. Pag kinukuha mo yung init, no, lumalamig ang surrounding. Ganun lang yun, no? So, evaporator, saan ba, gano'n ba kahalaga yung evaporator? Because doon nangyayari yung heat, no? Heat removal para maging vapor yung refrigerant and then magkakaroon ng cooling, no? Ito, it acts as a heat exchanger that transfers heat from the substance being cooled, no? Yung mga tubig, mga karne, no? Yung init doon mapupunta sa refrigerant tapos magbo-boil para papuntang evaporator. So now, where is the cooling effect, no, cooling effect being produced? Ayun, which part produce cooling effect in the refrigerator system or refrigeration system? So evaporator is the part of the refrigeration system that is doing the actual cooling, no, according to Google, no, doing the actual cooling according to the Wikipedia or yung mga journals. Because its function is to absorb heat into the refrigeration system, you don't from where you don't want. We don't want the heat from the meat, no? Sa meat, sa cold o sa ice na pinapalamig, ayaw natin yung init doon. So, i-absorb ng refrigerant na nasa evaporator. The evaporator is placed in the area to be cooled, no? Kaya yung ating evaporator, nandun yan sa harap, ibig sabihin, nandun yan sa kwarto. Hindi mo ilalabas, no? Ilalagay mo yung evaporator doon sa lugar na gusto mong palamigin. So, pag binaligtad mo yan, papalamigin niya yung labas. No, ba't mo naman papalamigin yung labas? Gusto mo namang sa loob. Hihiga ka para maging komportable and everything. Okay? So, the cooling is happening in the evaporator. Let me repeat that. Cooling, ang responsible ay evaporator, no? The air going to the space by boiling or evaporating the refrigerant flowing through it, no? This happens when warm air is blown across the evaporator as cold refrigerant moves through the evaporator coil. Kasi ma-absorb nga ng refrigerant yung init, lalamig na yun yung evaporator coil. Tapos may fan or blower, ibubuga niya. So may mga ducting, no, sa harap ng ating evaporator, no, sa kwarto. So malamig na, no? Ngayon, the next point I would like to summarize is how do we do the calculations in evaporator, no? So calculation. How do we calculate the evaporator capacity? So there are three ways to calculate the evaporator capacity, no? Yung heat, yung heat load or cooling load na inaabsorb ng evaporator, we can express them in three ways. First, let us say this is the heat, then we could get the mass flow flowing into the entrance or suction of the evaporator, then going out. It's just the same, right? Mass entering equals mass leaving according to first law of thermodynamics, law of conservation of mass and energy. So dito, delta H lang. change of enthalpy. It depends on the enthalpy, no? Normally, we use MH1, the higher energy, minus H4. Why? Lagay ko rito, no? So we have this we have this diagram. So this is 1. Superheated at the end of the compressor is 2. 3 is the discharge of the condenser, no? And entrance of the expansion valve. Expansion valve expands the refrigerant gas, no? Expands the refrigerant gas and it lowers the pressure at constant enthalpy. So ito yung 1. Ito yung 4. So ito yung evaporator, this is the evaporator, this is the condenser. This is the sorry, 4. No, ito 4, ito 1. This is the evaporator. So pag kinuha mo yung yung refrigerating effect at evaporator is what? H1, ito, H1 minus H4. Pag minultiply mo ng mass na pumapasok doon, magiging capacity siya, no, or load. Ang unit ng mga load ay tons of refrigeration, kilowatt, horsepower, o kaya BTU per hour. Let us check the unit, no? So, mass, enthalpy 1 minus enthalpy 4. Tingnan natin. So, normally, mass is given in kilogram per second. And HSH, no? H and H would result in the same unit, kilojoule per unit mass, no? Kilojoule per kilogram. So, canceled out, kilojoule per second. Anong kilojoule per second? Watts, right? So, how many watts in 1 ton? 3.516 1 PR, no? So, watts. Cancel yung watts. So, magkakaroon ka ng tons of refrigeration. So, yun yung una. That's the first one. How do we do the second? The second we could compute the evaporator capacity, no? Yung cooling load, yung i-absorb niya na heat in terms of the general equation for the heat transfer. What's that? M Cp delta T. O, check natin yung unit, no? Halimbawa, ito yung evaporator ko. Merong pumapasok sa evaporator na kilogram per second. Tapos yung Cp, depende yan sa material or substance. If it's water, no? If it's meat or beef or banana or fruit, no? Yung mga init ng prutas at mga gulay at tubig at karne, no? At ng isda, yun yung mga CP, specific heat, no? So ang unit noon ay kilojoule, kilogram, degree centigrade pwede rin, pero pwede rin Kelvin if you're going to make it absolute. Normally we are doing this absolute. So if that is Kelvin, you could also convert the temperature difference in Kelvin, no? So to be consistent and to cancel out the necessary units, no? So Kelvin and Kelvin will be cancelled, kilogram and kilogram will be cancelled, kilojoule per second will be left. So same thing, kilojoule per second is watts, no? Kilowatt. Joule per second is watts, kilojoule per second is kilowatt. Nagagawin mong kilowatts, no? So ang unit ay 3.516 o 3.52 na lang, 3.52 kilowatt 1 horsepower. So pangalawa yan. Now, pangatlo, meron tayong tinatawag na air coming from the tube, no? Sa evaporator. May mga sa evaporator kasi class may tubo, no? Ito, tubo. So ito halimbawa yung in or suction, ito yung out or discharge, no? So sa tubo na yan, meron kayong ika-calculate na papasok na hangin, no? Air entering, the temperature of air entering, na PE, no? Papasok yung hangin dyan, tapos sa loob ng tubo may refrigerant, na i-absorb nyo yung heat ng hangin, no? So, ano yung involved dito? Ang formula class ay Q, UA delta T or UAD, no? PD. Marami kasi ibig sabihin ko, no? Temperature difference, delta T, PD, temperature difference, or just D, difference, no? So, ang mangyari dyan, UAD, no? Ibig sabihin, ito yung unit natin, no? So, makakakuha rin tayo dyan ng, ng unit ng load or capacity because this one is overall heat transfer coefficient. No, magkakaroon tayo ng mga sample dyan mamaya. Huwag kayong mag-alala. No? So, overall heat transfer coefficient times the area times the temperature difference. So, if we are going to set the unit, no, set natin yung unit dito. So, Q equals UA delta T. Ito ay temperature. Sabi natin Kelvin. Ito ay area square meter. No? So, dito naman, meron siyang I think ganito, no? So, pag sa metric, watt, square meter, Kelvin, no? So, cancel yung area, cancel yung temperature, watts na lang. Okay? So, watts na lang, i-multiply mo, i-divide mo ng 1,000, magiging kilowatts. Pag kilowatt, i-divide mo lang ng 3.512. So, there are three ways to calculate the capacity in the evaporator, and we will have some formula for that. No. Now, another thing that we are calculating in the evaporator is the so-called COP. No? So, COP. Let me erase this. No? So, let me put here the evaporator capacity. Evaporator capacity. What is the formula? First is Q and delta H. No? Mass flow entering the evaporator and the change in enthalpy doon sa evaporator discharge and suction. No? Siyempre sa discharge, mas mataas yung energy. Number 2, Q equals what? And Cp delta P. Ito yung formula sa heat transfer. Number 3, Q is U overall heat coefficient times area times delta T or D. No? So, ano yun? Capacity. Refrigeration capacity or tinatawag natin cooling load. Cooling load or heat load. No? Pwede rin heat load. Product load. So, yun yung mga inaan natin. No? So, evaporator capacity. No? Evaporator capacity in terms of kilowatts. No? Now, another thing that we have to consider is this. Now, we can solve the COP. What is COP, class? COP is just the coefficient of performance, meaning refrigerating effect over power needed, no? Power input. So, meaning refrigerating effect over work, no? So, power or work of compressor or compression. So, paano ba yon? So, refrigerating effect is M, no? Yung papasok dun sa evaporator. Then, the higher energy in that evaporator is H1 minus H4 over the net work of compression. So, papasok doon ay mass din, na mass 1. Then, compression is what? Higher energy sa compressor is the discharge, H2 minus H1. So, yan yung coefficient of performance. No? Halimbawa, maraming evaporator. So, dito, refrigerating effect 1 plus refrigerating effect 2. Kung tatlo ay refrigerating effect 3. Kung maraming compressor, kukunin mo yung power ng 1. Di ba? Halimbawa, maraming compressor, no, ganito, dalawang compressor. Di ba? So, ito yung work of compression. Kukunin mo yung 1, i-add mo sa 2. So, ito namang refrigerating effect. Maraming evaporator. Ito, no? So, i-add mo. Refrigerating effect 1 plus refrigerating effect 2. Yun yung sa taas, no, sa numerator. Ang denominator is work of compression, no. Yung gagamitin na trabaho ng compressor para ma-produce niya yung capacity ng system, no, ng evaporator, yung capacity ng evaporator, no, na dapat gawin niya, no, yung para makapagpalamig siya, yun yung kukumpitin mo divided by the work of compression para magkaroon ka ng COP. Okay? So, ito 'yon, no? Bilang pag-uulit, just a review, I put all the diagram again here. Okay? So, ito yung pressure enthalpy, ito yung TS, temperature entropy. Okay? So, now we go to the types. If I ask you, class, what do you know about evaporators? What are the types in terms of construction, in terms of tube, in terms of surface evaporator, in terms of steam, no? So, yung construction, marami namang klase ng pagka-construct, no? It is given in a separate lecture, separate ang PowerPoint. Today, we are going to concentrate only in the evaporator, the calculation side, or the ones being calculated. This is more of a theory na elements, no? Ano yung mga klase ng evaporator, and so on. But ipapakita ko sa inyo yung mga pictures para may idea kayo. So, the question is, have you seen an evaporator aside from your refrigerator or from your aircon? So, there are other forms of evaporator. Look at this. No? So, this one is being used in the cold storage. Ano ba yung cold storage? Pwedeng mga karne, mga meat, ng baboy, ng manok, ng isda. Pwede rin naman sa mga iba, katulad ng sa mga halaman or sa mga semiconductors, no? Storage, no? Pag storage na ano na ito, sunod-sunod na tatlong evaporator, no? So nagiging komplikado na. Now to give you a brief background or to show you how does an evaporator look like, no? This evaporator is the evaporator for automotive, no? So if I'm gonna ask you, how many ports does the evaporator have, no? Di ba sabi natin merong suction at discharge, no? Kasi papasok din yung tubig, pang-evaporate kung tubig man. Sa kabila, meron ding suction saka discharge. Kasi nga, dalawa minimum of 2 medium or fluid ang kailangan nasa evaporator. So, 2 medium or media na fluid. Yan. Pwedeng tubig, papalamigin yung refrigerant. O pwede namang iba, no? So, evaporator yan. Ngayon, if I'm gonna ask you, where's the suction and where's the discharge? Where's the suction and where's the discharge? So, remember, suction is always has a bigger diameter, no? So, this one is bigger than this. So, the one which has a bigger, that is the suction, no? Suction part, because it was not labeled it, or it was also not declared, no? Here. So this one is discharge, no? Dapat mas malaki yung suction because it is the one supplying, and also it is designed so that it can compensate for the pressure loss or pressure drop. So the evaporator or the compressor or the expansion valve only operates ideally at the required pressure, but as the length is increasing, no? Pag inad nyo yan, no? Pag inad nyo yung length na yan, tapos kung ilang layer pa, ilang pass, so dadami na. So it requires time, and it requires it becomes having a loss, no? Pressure drop in terms of losses. So dapat yung suction will provide those losses. No, it should be capable enough to recompense all the losses so that the whole evaporator system can properly work. Otherwise, the longer the distance, the higher the pressure drop, bababa na yung pressure, magiging patak na lang o paano siya makakapagpalamig. So, depende yung pressure doon sa yung lamig, depende yan sa pressure ng system. No? May standing pressure, may running pressure. No? So, this is the evaporator for the split type. Ibig sabihin yung nasa loob ng ating kwarto, di ba ganyan? Wala lang balot to. No? So, eto naman sa Ford Explorer, no? Malaki. Malaki yung kanyang yung structure. So, again, this has higher diameter. Look at this, no? So, this one has higher diameter or bigger diameter. So, bigger diameter means yun yung suction. Ito naman ay discharge, no? This is the lower one, the smaller diameter, no? So, ito yung iba't ibang klase ng mga evaporator just to show you. Snake shape, no? Can, combing bent. Meron ding crimp pin, no? Meron din parang mga pako o bolt, stud. Ang tawag dito ay stud. Stud, no? Studded, no? Stud, no? Parang mga pako na nilalagay sa surface ng tubo ng evaporator. Now, the question is, why do we have this fin? Ang tawag dito lahat, class, sa ganitong extra na mga area ay fin, no? Pag past tense, fin, no? Fin tube, no? Why do we have this kind of thing, fin, no? Ito naman, square. Welded heat exchanger, square fin, no? No? Square. So, may square, may stud, merong mga micro channel. So, yun yung mga klase ng mga tinatawag na fin, no? Ano ba yung silbi ng mga fin? Ang mga fin class is to increase the heat transfer area. So, increase natin yung heat transfer area so that when the hot air comes, ito yan, mga evaporator. So, yung mainit na paligid, mainit na kwarto, mainit na karne, mainit na tubig, mainit na, o yung init galing sa gulay, when they come here, they are going to contact with more area. Pinarami yung area, no? Mas maraming area. Pag maraming area, mas malaki yung heat transfer. Tama ba? Is it correct? So, heat load or heat transfer area is a function of heat transfer, yung heat transfer, yung energy is a function of area. Look at the formula. U equals U A delta T. So, overall heat transfer coefficient ng isang bagay, no? Tsaka nung papalamigin, tas area, no? Ito yun. Yung mga area, yung bilog, siyempre business to, no? So, eto may mga area diyan papalakihin, tapos yung temperature difference. So, yung temperature ng hangin ay mas mataas kaysa dun sa temperature ng refrigerant na nasa loob. So, magkakaroon ng heat transfer, magbabago ng anyo, and then the energy will be released. So, yung tubong magiging malamig, no? Evaporator coils. In that case, magkakaroon ng fan, no? When the fan blows, makakapag-produce ng malamig na surroundings, no? Ang point natin ay fin. Ang fin ay para increase ang area so that the heat transfer will be efficiently done, no? So, heat transfer needs more area. So, may mga extra area dyan. No? Kung tubo lang, surface area lang ng tubo, no? So, ang ginawa mo, binalutan mo yung tubo ng fin, ng studded tube, and everything. So, yung hangin, dadapo doon sa maraming area and it will have a very effective or efficient heat transfer, no? So, there are other evaporators. Don't think na evaporators are just used in refrigeration. No. in sugar industry, no? For example, when I was in Africa, I was a consultant in a sugar industry, in the energy, in the transportation. So we visited the plant. Look at this, no? So this is called falling film evaporator. This is the rising film, meaning papataas yung flow ng hangin. Pag falling naman, pababa, magiging mga tinatawag na film, no? Yung water will become film, tapos pagbaba, malamig na. So, falling and rising. So, there are evaporators used in the industry like sa mga paggawa ng beer, alcohol, ng mga paint, di ba, ng mga gamot, ng mga pagkain, no? So, may mga evaporator. Ito tawag ito yung multi-effect evaporator, no? So, walang kinalaman to sa refrigeration, pero evaporator din, no? So, wala siyang kinalaman sa evaporator, pero sa air conditioning, pero evaporator din. So, maraming silbi yung evaporator. Now, we go to the uh, calculation, but before we go to this, let us go to the some configuration muna, no? There are configuration. Look at this. So here, look at this. How many evaporators do you see here? Ilang evaporator to, class? Ha? Ilang evaporator to? Dalawa, di ba? Dalawa. So, ang sabi dito, two evaporators and one temperature. So, another skill that I would like to teach you, or another skill that you should know, you should be able to acquire, is the this diagram, pictorial diagram, and translation to pH. How do we translate that to pH? Look at this. Gusto ko na lang i-translate, ha? So, we have a pH here. So where is the start of the process? So let us say the process starts at compressor, no? Ito ay evaporator. Meron tayong dalawang evaporator, no? Pero ang sabi diyan, anong temperature? 1, no? Ibig sabihin same. So if we are going to represent this into the system, same evaporator, of course dalawa yan, no? But in the pH, isa lang. Bakit isa? Kasi ito ay low pressure, ito ay condenser high pressure. Pag naglagay ka ng intermediate evaporator, ibig sabihin, iba yung pressure nun at iba yung temperature, right? Eh, ang sabi dito, it is stated in the problem that there is only same temperature. So here, constant temperature at constant pressure to, di ba? Constant temperature. Di ba sa pH ganyan? Ang temperature ay ito, di ba? So, constant pressure yan, constant temperature din, no? Pareho. Ito, constant enthalpy. So, hindi tayo pwedeng maglagay ng isa pang guhit kasi same lang, no? So, paano natin interpret yan? Sa compressor, ito, di ba, 1. Di ba, ito 1. Tapos, ito 2. Sa superheated. Tapos, papunta siya dito sa liquid line ng condenser. Nasaan na tayo? Ito, condenser. No, anong process sa condenser? 2 and 3. So, ibig sabihin, 2 and 3 is condenser. Dadaan siya sa expansion valve. How many expansion valve do we have? Only one. And the process is enthalpy is constant. This one is pressure is constant. This one entropy is constant. Then here, enthalpy, pressure again is constant. No? So, mangyayari yan, ang representation nito ay ganito lang din. No? Tapos, tataas. Yan. So, what if we have two evaporators and at different temperature? No? So, tingnan natin. Ilagay tayo dito. So, dito, pag magdadagdag tayo, now we will add 2 evaporators at different temperature. I think we already have this, no? Na-take up na natin. We already have this, no? 2 evaporators at different temperature, then, and 1 compressor. Right? So, I think we have already this. Now, i-paste ko na lang para makita nyo. Yung pinake up natin last time, meron tayo dito. Yung pina-assignment ko sa inyo, no? This one. Okay. Ilagay ko lang dito. Okay. Yan. Ito yung kanyang diagram, no? So, we already have solved this last week, no? I-emphasize ko lang. Mas mag-solve tayo ng ito. Yan. No? So, my question now is, where is the evaporator with the different pressure and temperature? So, here. So, we have evaporator 1. As you can see, it says 1. No? Evaporator 1. Evaporator 1. So, this one, no? So, evaporator 1. This one is evaporator 2. So, we have 2 evaporators, no? So, one is here and the other is here. Right? So, 2 evaporators yan. Ngayon, ano yung temperature niya? Sabi, different eh. Different temperature. So, ano yun? 0 degrees centigrade at negative 20 degrees centigrade. So, if the temperature is different, the pressure is also different. No? So, here at this evaporator, 293 halos. No? So, 293 kilopascal. Here, mas mababa ang temperature, mas mababa din yung pressure. No? So, 132.7 or sabihin mo ng 133 kilopascal. So, yun yan. Dalawa. Yan. No, dalawa. So, from here, 1 to 2 is entropy is constant, work of compression, 2 and 3. No? So, 2 and 3, nung mula dito sa 2 and 3, yun yung condenser. No? 2 and 3 condenser. Ngayon, ito naman, 3 and 4, ito yung expansion valve. No? So, 3 and 4 is the expansion valve. Right? So, 3 and 4 is the expansion valve. Ito yun, no? So, 3 and 4. Tapos, meron pa, 4 and 7. So, 4 and 7. So, constant enthalpy. Constant enthalpy. Yan. No? So, yan ay 2 evaporators at different temperature. Ngayon, ito naman, pangatlo. Nakalimutan kong yan. So, how do we label this? Ito yung pangatlo means 3. No? So, 3 evaporators at 1, 2, 3. 3 compressors. 1, 2, 3. No? So, tingnan natin. 3 evaporators and 3 compressors. Meaning, multi-compressors and multi-evaporator. Compressors. Right? So, paano yan? Nasaan yung mga yon? So, eto, 3 evaporators, saka nandyan din yung formula. So, last week, nakapag we already have considered the 2 evaporators and 1 compressor. Now, we already have those calculations. I already forwarded the PowerPoint to you. So, here, we have to find out where are the evaporators. Look at this. No? So, eto, evaporator. No? Ito naman, ano to? Condenser. No? So, ilan yung mga compressor? 3, di ba? Yan. 2 and 1, 4 and 3, tsaka 6 and 5. No? So, yun yung mga compressors. So, maraming multi-compressors. There are different compressors and there are multiple evaporators. So, compressor. So, how do we get the refrigerant? We have to get the refrigerant so that we can get the capacity, no? So, the cooling capacity of the system is this, no? You have to add the 3 refrigeration effect. So, look at this, tinan mo. 1, no? Evaporator 1, meron kang mass 1, meron kang mass H1 minus H12, di ba? So, yun. H12, ayun. Then, kunin mo naman yung evaporator 2, kunin mo yung mass 2, dumadalo yan sa evaporator na to. Ano yung pinaka-higher energy? 3 and 10, between 3 and 10. So, ano mo yung 3, saka 10, no? And then, dito naman sa evaporator ng number 3, 5, tsaka 8, no? So, dito. Yan. Yan. So, yan yung mga kunin mo, no? Or, pwede mong kunin pala ito hanggang 9. So, basta mag-energy balance ka. No? So, dito yung mga points ng energy balance nyo. No? So, eto yun. Paano mo makukuha yung yung refrigerate ay yung tawag doon, yung power input. So, eto, no? So, power input, eto, tatlo yun, no? 2 minus 1, no? H2 minus H1. Bawat power or gawa ng compressor, no? So, mass entering in that compressor, H2, and then multiply by H2 minus H1. The other is mass of that evaporator o yung sa linya na yon, ito, papunta evaporator, di ba? Yung evaporator, papunta na naman, itong dulo ng evaporator, papunta sa compressor. So, H4 minus H3, saan yun? H4 minus H3. So, we have to see the H4 and the H3. So, erase natin ito para yan. So, dito na tayo. Evaporator 2 is H4. Ito yun. So, compressor 2 pala. Compressor 2 is H4 minus H3. Then, compressor 3 is H6, no? Minus H5. So, ito yun. H6 minus H5, no? So, pag nakuha mo na lahat ng work of compression, then kunin mo yung refrigerating effect ng 1, ng 2, tsaka ng 3. Saan yun? Ito yun, no? So, the refrigeration effect of this, refrigeration effect of this, and the refrigeration effect of this. No? Ipapag-add mo yan, then i-divide mo sa work of compression na pinag-add na natin yung mga nag-negotiate. No? Dito natin i-add sa work of compression bawat isang compressor. Ito naman bawat isang evaporator. No? So we will get the coefficient of performance. Okay? So now we will consider this saan ba yun? Ito. Yung sinolve natin kanina, how last week, no? How do we get the refrigeration capacity if the enthalpy is given, no? Capacity of refrigerator, ito lang 'yon, no? So refrigerating effect 1 is mass of evaporator 1 minus kung ano man 'yon, no? Kung ano mang enthalpy 'yon. Tapos refrigerating effect 2 is mass ng evaporator 2 times the enthalpy. So tingnan natin dito sa diagram. Yan. So, kung ito yung pH natin, ito yung ating 1, no? Halimbawa, ito yung ating 1, ito yung ating 2. Tama ba yung designation natin? 1 tsaka 2, tama, no? So, this evaporator is 1, this is 2. So, how do we get the refrigerating effect? No, sundan ko lang to. So, how do we get the refrigerating effect nito? So, the refrigerating effect is what? Of evaporator 1 is mass of evaporator 1, yung pumapasok dito, no? So, from here, from saturated here, yung pumapasok rito na mass. Na? Tapos mamaya, yung pumapasok rito na mass, no? So, binigay naman sa problem, no? What is that mass sa evaporator 1? Ayan o, nakalagay. The mass flow rate of refrigerant entering evaporator 1 is 0.2095. Ito, 0.2095. So, ito, ang gagawin mo lang, lagyan natin dito, no? So, refrigerating effect 1 is mass evaporator 1 times H, ano, 5 minus H4. No? So, refrigerating effect at 1 is mass, no? So, 0.02095. Ito yun. No? So, this one, 0.02095. Yan. So, 0.02095. Meron tayong lagi na, ano, na, yan. So, 0.02095 H5 minus H4. No? So, hanapin natin. Binigay naman dito eh. H5. Where's H5? Ito. So, punta tayo sa 5. No? H. Diba? Ito yung H. Oh. So, enthalpy at 5. This one. Enthalpy at, ano pa isa? 497. No? So, this one is 2 minus 97. Ano yung ano? H5? H5. 247.23. So, 247.23. So, multiply mo rito, magkakakuha ka ng kilowatts, no? Kasi ito ay kilogram per second. Ito naman ay kilojoule per kilogram. So, it will be cancelled out. Kilojoule per second is kilowatt. Tapos, divide mo siya ng 3.75 na kilowatts 1 CR. So, makakuha mo yan. Okay? So, ngayon, punta ka naman doon sa isang refrigeration effect, number 2. Ito na, so refrigeration effect, number 2 will be the mass flowing into the evaporator 2, which is here. At 0.7, lalabas sa 8. I-multiply mo siya sa difference ng enthalpy nila, no? Which is higher is H8 minus H7. So, titingnan mo ngayon yung mass entering the evaporator 2. I think nasa problem, ang sabi dyan ay the flow rate entering evaporator is 0.024. So, you have to plug in, no? Just direct plug in 0.02024 multiplied by H8 minus H7. So, ano nangyari yun? Dito, no? So, sa number 2, H8 minus H7. So, kukunin mo yun yung H8 saka H7, nasa table naman na binigay, na? So, nasa yung H8? Ayun. So, ito yung H, na H8. Ito yung 8, di ba 8? Ayun, 8. Ito yung 7. Same as dun sa kanina, no? 97. So, 235 minus 97. So, dito sa RE2, no? Ilagay ko lang dito. So, 235 minus 37. Kasi ito yung mass, 0.02 kilogram per second. Tapos ito, kilojoule per kilogram. So, kilogram will be cancelled, then kilojoule per second. So, it's kilowatt. So, if you are going to compute in terms of ton, so RE1 will be 0.9 tons of refrigeration. RE2 is 0.8, no? Tons of refrigeration. So, pareho na silang tons of refrigeration. Okay? So now, I'm giving you, paki-screenshot to, no? Paki-try solving, no? Habang siguro mga 5 minutes. Meron pa tayong 5 minutes. Pakilagay lang yung given class. Pakilista lahat ng given and yung formula para makuha yung refrigeration load. Saan kinukuha yung refrigeration load? Sa evaporator, no? Sa yung lahat na aabsorbin ng evaporator. Lahat ng init na i-absorb ng evaporator, no? Diyan sa room na 'yan. Okay? Tapos ano yung formula nun? No, siyempre MCP delta T lang 'yon kasi meron siyang mga ito. Tingnan niyo, yung room. Ayan, no? Meron siyang karne, meron siyang ilaw, no? Merong mga surroundings na init, no? Sensible heat, mga load, tapos kung ano-ano pang mga init diyan, i-absorb lahat 'yun ng evaporator, kaya may Q evap, no? So paki-copy lang 'to, paki-screenshot. What is the refrigeration load of the chilling room? The chilling room, and what is the volume flow rate of air? Ano yung kailangan na air? Napakahalaga niyan, no? Kasi pag hindi mo kinumpute yan, saan dadaan yung hangin? Hindi mo alam kung ilan yung dadaan na hangin sa evaporator coil para mapalamig niya. So, napakahalaga ng CFM, cubic feet per minute, or yung tinatawag na volume flow rate, no? Cubic feet per minute class ay ano yun, English, no? Pag metric, liter per minute. Tapos heat transfer area. Ilan yung heat transfer area na nasa evaporator? Yung meron siyang mga fin, di ba? Fin tubes. Maglalagay ka ng fin tubes, no? Sulat lang muna yung given tsaka required formula. Tatlo lang na refrigeration load sa chilling room, yung mga i-absorb niya na init ng evaporator, the volume flow rate, yung buong ano ng hangin na papasok, tsaka yung heat transfer surface area. Formula lang. So, ilagay lang yung mga given, mga data known. So, my instruction is this, no? Please jot down all the given, mga data given to us. And then, yung mga formula based dun sa tanong. So, what are the questions? Refrigeration load. Ano yung load, no? Siyempre, i-absorb yan ng evaporator. Nakita nyo naman yung, so, try to look at the figure, no? So meron tong evaporator. Ayan, no? Evaporator, i-absorb niya yung mga heat, di ba? Kita niyo ba ito? So yung heat ng karne ng ano ba to? Baka, i-absorb niya. Yung mga ilaw, ilan 'yon? Ito. 3 kilowatts i-absorb niya. Yung mga surroundings, ano 'yon? Yung wall, no? Yung init ng wall, ng hangin, ng kung ano-ano diyan, labas sa pasok sa pintuan, i-absorb yun ng evaporator. Pag inabsorb niya yon, pupunta yung init sa refrigerant. Magbo-boil yung refrigerant, magkakaroon ng tremendous release of energy. Ibig sabihin, yung refrigerant from liquid naging gas, na naging vapor. So, absence of heat dahil na-absorb ng refrigerant, magbubuga siya ng malamig. Kaya nga ito, no? So, yun yung evap. No, kung ano yung na-absorb niya, yun yung ibubuga niya rin na lamig. Kasi kinain niya yung init eh. So pag absence of heat, magiging coldness, no? Tapos iaano ng fan. Ito. Itulungan siya ng fan na ibuga, so magiging malamig sa chiller. Kaya nga chiller room 'to eh, di ba? Chiller room. So paki-screenshot eto. Paki-screenshot ng mabilis class. Screenshot na ba? Screenshot na. So, pag na-screenshot na, punta kayo dito para naintindihan nyo yung solution. Tapos pag-usapan natin lang ng mabilis kasi mag-oras na rin, ha? So, tingnan natin. Dito. Yung solution. merong inassume dyan yung rate ng evaporation na no? Rate ng water, evaporation ng water. 0.08 kilogram seconds. Mahalaga yan. Water evaporates at 0.08 kilogram per second. So, screenshot to. Screenshot. Paka-screenshot yung solution. Tsaka, eto. Yan. Para alam natin kung anong ginagawa natin. Kasi A and B, eto na yung answer eh. Okay? So, ililipat ko ulit dito sa first, no? So, i-analyze nyo kung paano. I'll give you 3 minutes, tapos i-discuss natin ng mabilis lang, ha? Mabilis. Hello class, discuss na natin ano lang, kahit mga 10 minutes, no? So, yung first question, ano ba yung first question? The refrigeration load of the chilling room, no? So, ibig sabihin, pag sinabing refrigeration load, yun yung heating load, no? Or yung load na kailangan na i-absorb ng evaporator, no? That is refrigeration load, no? Saan nangyayari yung cooling load or yung refrigeration load? Sa evaporator. Yun ang i-absorb ng evaporator dahil yung evaporator ay may tubes, nandun yung refrigerant, di ba? Bakit refrigerator? Kasi yun din ang nagpapalamig. Pag hinigop niya yung init, ibubuga niya yon sa pamagitan ng lamig. No? Kaya nga sabi ko sa inyo, hindi lalamig yung isang bagay kung walang init. Kasi kailangan niya munang i-absorb yung init bago niya mapalamig. Parang sa air conditioning ng room. Yung init ng tao, yung init ng room, yung init ng mga furniture, ng tela, ng kama, ng mga walls, i-absorb yun ng evaporator ng air conditioning. Yung window type, yung box type. So, higupin yun, yung init. na pagka nahigop niya, and due to evaporation, refrigeration system, yun din ang ibubuga, no? Based on that, yun ang ibubuga niya na lamig para ma-compensate, no? Mapantayan niya yung init na inabsorb niya, dapat maibuga niya yung lamig, no? So ganon. So ito lang, refrigeration load of the chilling room. When we talk about the refrigeration load, ano yung mga load? Ano yung mga kukuhanan natin ng init sa room? E di tingnan natin yung room. So ito yung room natin. Yan, no? Ano ba ang makikita nyo sa room? Ano yung mga load? O, ilaw. Ilan yung lights? Ilagay ko lang rito. Ilan yung load ng lights? 3 kilowatts. Yung surroundings, no, ito, yung surroundings, yung load sa surroundings, ibig sabihin yung mga wall, yung mga pagbukas-bukas ng pinto, no? No? So 13 kilowatts. Ano pa? Yung mismong carcass. Ano yung carcass? Yung patay na beef, no, pag kinatay mo dun sa ano, sa katayan, no? Siyempre mainit pa yan, 'di ba? Dating buhay eh. Kapapatay lang. So beef carcass. Okay? So 285, no? Titingnan mo kung ilang oras, yung time, no? Tsaka anong specific heat. 'Di ba? Ngayon may load pa rin yung iba, no? Yung ano to? Yung fan, no? Ano ba to? 26 kilowatts, no? No, so ano ba to? Ito yata yung sa beef, no? Sa kilowatt, no? So tingnan natin kung paano siya kinompute, no? Tingnan natin dito. First, we consider the specific heat. Natin nyo. Kinalculate na lang dito yung specific heat. In-adjust na lang kasi ito ay 1.68 times 2.51. Ano ba yung 2.51? So yung 2.51 ay yung specific heat ng sa tubig. Ano ba ito? 2.51, no? So tapos yung water content nilagay din, no? So 1.68 plus 2.51 nasa table kasi yan, no? So ito na lang ang kinuha. Specific heat is 314 kilojoule per kilogram degree centigrade, no? So ngayon mag-umpisa tayo. Let's start with the beef, no? Ilan ba yung beef? Ang sabi, ilan ba yung beef na pinatay? Ilan yung baka na pinatay? Carcass, means dead body. Dead animal body is carcass. 450, no? Bawat isang baka, ilang kilo? 285. Ayan, no? Di ba? 285. Makikita niyo yan sa problem, no? Ayan, no? 285 ang average ng kilo, no? Tapos yun namang capacity ng chilling room ay 450. 'Di ba? Ayan, 450 na patay na baka na nakabitin, nakasabit. Ito, no? So, yan. Tapos yung mga lights, no? Power consumed by the fan. No? So, fan. Siyempre, mainit yung fan, no? May motor yun eh. So, 26 kilowatts. Ayan. Ano ba tayo? Ayan, 26 kilowatts. Tapos yung lights ay, ito yung fan, 26. Yung 3 kilowatts light. Yung fan ay 26. Tapos yung kapaligiran, no, envelope. Yung mga bakod, mga wall, no? Doon, mga bintana, 13 kilowatts, no? 13 kilowatts. Ito, 13 kilowatts. Yan. So, yun, ito total natin yung class. Ang mangyayari, ito, no? We start with the beef. How do we compute for the beef? We have 450, no? 450 na mga baka, 285 kada baka. Tapos, i-divide natin ng 10, no? Kasi per timing, no? Kasi mass flow eh. Mass flow ng heat. Eh, ilang oras ba siya papalamigin? No? 10 hours. Ito. Di ba? After they wash, pagkatapos sinugasan yung mga baka, kailangan silang i-cool sa 15 degrees centigrade mula sa 36 degrees centigrade na temperature sa room, no, 10 hours. Yan. Ito. So, 10 hours, i-divide mo sa 10 hours. So, i-divide mo sa 10 hours, no? Kaya lang, hindi naman hours ang ano natin, seconds, no? So, if we have 10 hours, no? So, 10 hours para makancel yan, di ba? 1 hour is 3,600 seconds, no? So, para makancel, ito pala, 1 hour, no? So, 1 hour is 3,600 seconds. So, cancel yung hour at hour, magiging kilogram na lang to per second. No? Ayan, 3.56 yung mass flow rate ng beef, no? Na energy ng beef. Ngayon, ang next natin, paano natin kukunin yung heat sa beef? Kasi may mass flow na, di ba? Ng air, ng init, no, dadaloy sa katawan ng beef papunta sa tubing ng evaporator. So, ang formula natin ay mCp delta T. So, yung M natin na-compute kanina, 3.56 kilogram per second. No. I-multiply natin siya ng specific heat, no? Pag tinotal mo yung specific heat kanina, ginawa na dito sa 3.14, no? Kasi pinag-add na, may table kasi nasa Sengel, hindi ko na nailagay, no? So ito 'yon, 1.68 plus 2.51 plus yung water content, no? Sa total 3.14 kilojoule per kilogram, degree centigrade or Kelvin, no? Sa 3.14. Ito 'yon. No? So, pwedeng Kelvin, pwedeng centigrade, wala nang problema yon, no? So, ito ay kilojoule per kilogram. Sabi mo na degree centigrade. Tapos yung delta T, ano yung delta T? 36 to 15, no? Kasi ang initial ay 36 tapos 15, na makikita naman diyan, no? Para malinaw, i-erase ko lang, no? So, ito lang ang i-consider natin kasi time naman, no? So, ito lang. 36 tsaka 15. Kasi yung room ay 36, i-cool mo siya sa 15. So, may delta T siya. Yan. No? So, 36 times 15. Minus 15. Yan. So, ito yun. No? So, 3.56 times 3.14 36 minus 15. Makakakuha ka ng 235 kilowatts sa beef pa lang. Sa beef. No? Ngayon, i-add mo yung mga iba pa. Yung fan. Ilan yung fan? So, ito ay 235. Ilagay ko rito, ito. 235 sa beef. Sa fan ay 26. No? Kasi may motor yung fan. Iinit yan. Yung lights, mga ilaw, ay 3 kilowatts. Tapos yung heat gain sa paligid, no? Heat gain ang tawag doon, sa surroundings ay 13. So, i-add mo yan. 235, 263 plus 3 plus 13, no? 235 plus 26 plus 3 plus 13, 277. Yun yung total sa room, no? Total sa room yon. Kasi ito beef lang eh. Ito yung total sa chilling room, no? So, yun. The amount of carcass cooling due to evaporative cooling. Bakit nagkaroon ng evaporative cooling? Kasi may rate, no? May rate kasi class yung yung beat, no? 0.08 yung kilogram per second, yun yung rate ng tubig, no? Na nagpapalamig sa chiller, no? Water evaporates at a rate of 0.08 kilogram per second, no? Paano nangyari yan? Kasi sabi doon, yung baka, no, papalamigin siya ng chilled water, no, at yung portion ng mga iba pang pagpapalamig ay napunta doon sa evaporator, no. So ang mangyari diyan, 0.08 times 2490 kilojoule per kilogram, no. So 2490 kilojoule per kilogram, so makakakuha tayo ng ating beef na evaporative naman, no? So pag kinuha mo 'yan, yung mass ng air naman, no, mass flow air kasi ito mass flow rate ng water 'to eh. No, ito ay mass flow rate ng tubig, 0.08, no? So dito naman is mass flow rate, no, ng tubig ng air, no? Ito ay 277, no, ng Q ng air over CP delta T. Ito yung CP specific heat ng air. Ito yung delta T ng air. No, paano nangyari yon? Negative 2, di ba? Negative 2, malamig yon papunta sa 0.7. Ito yun. No? Sabi dito, ayan. Temperature of the air rises from negative 2. Siyempre, mas malamig yan, papuntang 0.7. So, dapat yung parang pinaka-total na quantity niya lang, no? So, negative 2, no? Tapos, ito ay 0.7. So, mangyari, mas mainit yung 0.7, no? Delta T. 0.7 minus yung lower, negative 2. So, magiging plus, no? So, magiging 2.7. Magkakaroon ka ng mass of air na 102 kg per second, no? So, ngayon, paano mo gagamitin mo yon sa volume of air, no? Kasi density is mass over volume. So, yung volume is mass over density. So, anong mass? Ayun, no? Kasi ano na to, time, no? 102 kilogram per second, no? Tingnan mo rito. Yan, no? 102. Yun yung mass. Mass ng air is 102. Tapos yung density ng air is eto, 1.292 kilogram per second. So magkakaroon ka ng volume na ganito, no? 78.9, no? And the rest ay mga calculations na lang, no? So ngayon dito nagkaroon tayo ng heat removal sa evaporator kasi ang sabi doon merong mga na frozen, no? Merong mga na frozen na yellow dun sa evaporator. Ang sabi doon, you know, also banggitin dito, no? The heat transfer surface area, yung letter C, the heat transfer surface area of the evaporator on the air side, assuming all the vapor and fog in the air freezes in the evaporator. So yung mga lamig, yung mga hangin, yung mga hamog na frozen siya sa evaporator. So mangyari doon, kung gusto mong palamigin 'yon, no, magkakaroon ka rin ng heat release doon. Ibig sabihin yung yellow, no, mapupunta yun sa 0, tapos yung 0 mapupunta sa tubig, no? Ulitin ko, yung ice na likom na collect sa evaporator mapupunta sa 0 na ice. From 0 na ice mapupunta sa 0 na water. So magkakaroon tayo ng heat of fusion. Ano ba yung heat of fusion? Yun yung 334, no? 334. Mamaya maipapakita 'yon, no? So ito 'yon. Therefore the total heat ito, yun. Pakitingnan lang to class, no? Q freezing. Ito. Sabi kasi rito, no, frozen as a temperature drops to negative 2 and the evaporator must also remove the latent heat of freezing, no? So kasi meron tayong tinatawag na heat, latent heat of vaporization, ibig sabihin yung yung tubig na mainit magiging vapor. Ito naman latent heat of freezing or fusion, no? Latent heat of freezing or fusion, yung yellow magiging tubig. Ayan, no? So dito 0.08 kg per second, no? 0.08 kg per second yung rate ng tubig, tapos ito yung latent heat of freezing or fusion, no? Di ba standard naman yon? 334 N. Pakita niyo. No? The latent heat of fusion of water and the vaporization is this, no? So latent heat of fusion, ito 337, ni-round off na lang. Ito. No? 333.7, ginawa na lang 334. Ito naman, vaporization is 2,501 kung sa tubig. No? So yung tubig para mag-vaporize, kailangan niya ng latent heat of vaporization kasi ano siya, no, naging latent heat. Latent heat, walang change ng temperature pero may change ng phase. So pag nag-change yung phase, hindi mag-change yung temperature, kaya ito lang ang kinuha natin, no? Ang kinuha natin ay ito lang. Etong 334 latent heat of freezing. Latent heat of freezing at the rate of ng water is 0.080 kilogram per second. Saan mo nakuha yon? In-assume dito sa una pa lang, ayun, no? Water, di ba? Evaporates at a rate of 0.08 kilogram per second. So yung mula sa yellow, naging tubig. Kaya nag-release siya ng ganun na energy na 334 or 333.7, no? So eto yon. Inano na lang ni round off. Yan. Nasa 27 kilowatts yung sa freezing. So ang gagawin mo sa 27 kilowatts, i-add mo sa cooling load. Ano tong cooling load? Ito yung sa baka, yung sa fan, yung sa ilaw, no? Yung surroundings. I-add mo pa yung energy due to latent heat of fusion or freezing. No? Fusion is freezing. Pag in-add mo na yan, makakuha ka ng 304 kilowatts. I-convert mo sa watts. 304 kilowatts is 304,000 watts. Para makuha mo yung area, di ba? Di ba ang formula natin is Q UA delta T, di ba marami tayong formula sa pagkuha ng heat. So meron tayong heat, eto na yon, no? Eto yun, no? 304 kilowatts. Lalagay ko lang 304 kilowatts or 304,000. Yung U is constant, no? 20 watts per square meter. Ito yung constant ng heat transfer constant, no? 20 watts per square meter. Area, yun yung pinapahanap. T, yun yung temperature difference, no? Ang temperature natin difference ay yung 5.5, no? 5.5 ang ating delta T doon sa tinatawag na pinapakompute sa atin yung area, no? So kailangan natin ng delta T para doon sa makuha natin yung area na papasukan ng hangin, no, para makasalamuhan niya yung mga evaporator tubes, no? So pag kinumpute natin yan, class, no? Pag kinumpute natin yan, eto yun, no? So kung ang formula ay QA, Q, no? If the formula is Q, UA, delta T, so magdi-divide ako dito ng U, magdi-divide ako dito ng delta T, no? So makaka-cancel na yon. Yung U mawawala, delta T mawawala. So Q, eto yon. Q, ito yun. U, universal constant ng heat transfer, no, due to convection. Ito yun. No, pag ang pinag-uusapan ay beef, no? Tsaka mga ano sa chiller. Ito naman ay delta T, no? So magkakaroon ka ng napakalaking area. Tingnan niyo, 2 kilometer. Grabe. 2.764 kilometer, no? Kilometer square or 2,764 square kilometer. Napaka-large ng area, no? So, kailangan siya ay finned. Yung kanina, yung tubo ng evaporator, babalutin natin ng mga metal. Ang tawag doon ay fin. Ang plural ay finned, no? So, sabi diyan, a finned surface must be used to provide such a large surface area. So, kailangan ng ganitong area, gagamit ka ng mga finned tubes, finned, para ma-perform mo tong gantong system. Napapalamigin niya yung beef, no? Yung carcasses na 10 oras at ganitong mga kilo, no? So yan yung isang paraan para maka-compute ng cooling load, no, sa chiller or sa evaporator. So ganun muna, i-stop ko muna tong ano, no. Itutuloy na lang natin. So ang last na lecture natin ay sa Webes. We are going to take up yung chiller naman, no? Chiller. Na umpisa na natin, 'di ba? Chiller yung kinompute natin ngayon. Pero sa chiller kasi nandun yung evaporator, no? So chiller is a complete system. May compressor, may condenser, may evaporator, may expansion valve, no? So yun yung ating munang class ngayon. So I'll abandon this yung muna ang lecture. Sorry sa ano,